Remember when we explored the original transformer in hashtag TCM183000? It fundamentally changed how we thought about processing sequences, especially in language, by introducing self-attention. It allowed us to consider relationships between all parts of a sequence simultaneously, rather than sequentially. It was a true breakthrough.
Yes, it showed us that models didn't need to process words one after another, that parallel processing was possible, which felt like magic for speed and efficiency.
Before the transformer, the dominant sequence transduction models relied heavily on what we now call legacy architectures, like recurrent or convolutional neural networks. They were effective, but had limitations, like RNNs struggling with long-range dependencies due to vanishing gradients, and CNNs being inherently local in their receptive fields.
Right, especially with long sequences, RNNs struggled with information flow, and CNNs were designed more for local patterns.
The key innovation was this bold claim, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. It was a radical departure, proposing that we could get state-of-the-art results by completely abandoning these established sequential processing paradigms. This was a paradigm shift.
So they were saying attention is all you need, literally. No more sequential processing, no more fixed size windows, just dynamic relationships.
And it worked. The transformer showed superior in quality while being more parallelizable and requiring significantly less time to train. This efficiency was a huge win for NLP.
That's the part that really hooked everyone. Better results, faster training. It's what every new architecture aims for. The original paper focused on machine translation, which makes sense for sequence transduction. But I remember from hashtag TCM213005 that transformers now do vision too. How do you go from translating sentences to understanding images?
That's exactly the question we'll explore today. It seemed counterintuitive at the time to apply something developed for sentences to something as visually rich and spatially structured as an image. If attention is all you need for language, can it truly be all you need for something as structurally different as an image? It's easy to think of language and vision as completely separate problems with distinct solutions, but the transformer suggests a unifying principle: sequence processing. Its insight is that if you can represent any data, whether words, pixels, or even sensor readings, as a sequence of discrete tokens, then its attention mechanism can find meaningful relationships within that sequence, regardless of the original data type.
So the sequence part of sequence transduction is more general than just words, then. That's a shift in perspective.
Exactly. Think of it like this. An image, just like a sentence, can be broken down into smaller, ordered pieces. In a sentence, these are words. In an image, we can treat them as fixed-size patches of pixels. Both become sequences of tokens that the transformer can process. However, unlike words in a sentence, image patches inherently have a 2D spatial relationship that isn't immediately obvious from a flat sequence. The transformer will have to learn this, or will have to encode it specifically. The challenge is making those pieces meaningful for a transformer.
Like pixels or maybe groups of pixels? But how do you make them look at each other effectively without convolutions?
That's where the core intuition of the transformer comes in. It's not about the nature of the elements, but the learned relationships between them and how we preserve their order. Let's dig into that intuition now.
Okay, let's build up the mental model of how attention functions at a high level first, and then how it handles order.
This article, The Illustrated Transformer, is a fantastic resource for building intuition. It reiterates that the transformer, a model that uses attention to boost the speed with which these models can be trained.
And not speed is directly tied to its parallelization capability, right?
That's what we learned in hashtag TCM183000. Attention allows calculations for different parts of the sequence to happen simultaneously.
At a high level, the transformer still follows the classic encoder-decoder structure: an encoding component, a decoding component, and connections between them, albeit with a very different internal mechanism.
So the overall architecture is familiar, but the internal mechanisms are what change the game by removing recurrence.
The core of the encoder is the self-attention layer. It helps the encoder look at other words in the input sentence as it encodes a specific word.
This is crucial for context. Instead of just seeing one word, it sees how that word relates to all others simultaneously. It's like reading a whole paragraph to understand a single word, but instead of relying on our prior knowledge of grammar and meaning, the model learns these relationships from data.
But there's a critical piece missing when we dispense with recurrence and convolutions entirely. Self-attention tells us what to focus on, but not where it is in the sequence. Without sequential processing, how does the transformer know the order of words? This is where positional encoding comes in. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence.
So it's an explicit addition, a signal that says this word is at the beginning, or this word is before that one, effectively giving the model a sense of left to right or spatial location that's otherwise lost when you just treat everything as a bag of words to attend to.
Exactly. It's a clever trick. We add unique, fixed patterns of numbers, these positional encodings, to the input embeddings of each word before they hit the self-attention layers. This way, each word's embedding gets a little position tag that the network can learn to interpret. For images, when we flatten patches into a sequence, this becomes even more vital to maintain spatial context.
That makes sense. Without it, apple bites cat would be indistinguishable from cat bites apple if attention was the only mechanism. It's how the transformer keeps its bearings in a sequence.
Now, armed with self-attention and positional encodings, let's look at a concrete example. Consider the sentence, "The animal didn't cross the street because it was too tired." If we ask, what does it in this sentence refer to? It's clear to us.
To a human, it refers to the animal. Our human brains effortlessly link it to animal using common sense and the surrounding words. But for a traditional neural network, that's a difficult ambiguity to resolve without long-range context.
This is where self-attention allows it to associate it with animal. It learns to weigh the importance of other words, like animal and tired, when encoding it.
So the model isn't just looking at the word it in isolation, but dynamically drawing connections to other words to enrich its understanding.
It's dynamically creating connections. It's not just a fixed window, but a learned focus on relevant parts of the input.
If you know RNNs, think of how maintaining a hidden state allows an RNN to incorporate its representation of previous words. Self-attention does something similar, but in parallel. But crucially, an RNN's hidden state aggregates information sequentially, while self-attention processes the entire sequence in one go, allowing any word to influence any other, regardless of distance.
It's like the RNN's hidden state can see the whole sentence at once, not just what came before. That's a huge difference in how context is built.
It's not just looking up information, it's learning an interpolation or weighting. The strength of the connection or attention is learned, not hard-coded.
Right, it's not a rigid rule-based system. It's a nuanced, data-driven weighting. The model discovers which words are most relevant for understanding the current word. So it's not simply animal has a high score. It's that animal contributes heavily to the new representation of it, based on how the model has learned to process tired and street.
This intuition of learned relationships and explicit positional awareness is powerful. Now, let's get into the actual mechanics of how this looking and associating happens using vectors and matrices.
Okay, from the high-level concept to the mathematical steps. I'm ready for the query, key, and value breakdown.
The first step in self-attention is to create 3 vectors from each of the encoder's input vectors. These are the query, key, and value vectors.
And these input vectors are the word embeddings combined with the positional encodings we just discussed, right? So for every word in our input, we get 3 new vectors. What's the intuition behind these names? Query, key, value sounds like a database lookup.
That's a good analogy for intuition. Think of the query as what you're looking for, the key as how you match it, and the value as the information you retrieve. Where it differs from a traditional database is that here our query doesn't just find one exact key. Instead, it softly matches against all keys in the sequence. And the value we retrieve is a blended combination of information from every value based on those soft matches.
Okay, so my query for it would scan all the keys in the sentence to find a soft match and then pull out a blended value from the best matches. It's a continuous weighted lookup.
These Q, K, V vectors aren't random. They're created by multiplying the embedding by 3 matrices that we trained during the training process. These matrices are learned parameters of the model. So the model learns how to generate these specific query, key, and value perspectives for each word based on its input embedding. The looking part is actually learned.
Next, the second step in calculating self-attention is to calculate a score. This score tells us how much focus to place on each word in relation to the current word.
So it's quantifying that relevance we talked about earlier. And how is that score calculated? Is it directly the query-key interaction?
Precisely. The score is calculated by taking the dot product of the query vector with the key vector of the respective word. A higher dot product means more similarity, more relevance between the query and key.
So it's a direct measure of how well a specific query, example, it, aligns with a key, example, animal, allowing us to quantify the semantic relationship. If my it query has a high dot product with the animal key, that means they're relevant, and animal gets a higher score for it.
After the dot product, we divide the scores by 8, the square root of the dimension of the key vectors. This scaling helps stabilize gradients during training. Without this scaling, large dot products could push the softmax function into regions where its gradients are extremely small, slowing down or even halting learning.
It prevents the dot products from getting too large, which could make the softmax function's gradients vanish, a neat trick for training stability.
Then we pass the result through a softmax operation. Softmax normalizes the scores so they're all positive and add up to 1. These are our attention weights.
So these normalized scores directly tell us the percentage of attention to give each word. These attention weights are effectively the how much to pay attention to each word, right? The percentages of focus. This is the interpolation mechanism we talked about.
Finally, the 5th step is to multiply each value vector by the softmax score. Then we sum these weighted value vectors to get the output of self-attention. This final sum becomes the new, contextually enriched representation for that original word. It's a blend of information from the entire sequence, weighted by how relevant each part was.
So the query and key determined how much to pay attention, and the value vectors are what information gets blended in. And by summing them up, we get a single context-rich output vector for that word. That's incredibly elegant.
While this self-attention mechanism is incredibly powerful and generalizable, it's important to acknowledge its practical limitations. For instance, the original transformer's attention mechanism has a quadratic complexity with respect to the sequence length, meaning very long sequences can become computationally expensive. Furthermore, models like ViT, which replace CNNs, often require very large data sets for pre-training to achieve their superior performance, a significant resource investment not always available.
So it's not a silver bullet for every scenario, especially where data is scarce or sequence lengths are extreme. It trades off some of the inherent inductive biases of CNNs for greater flexibility, but demands more data to learn those patterns from scratch.
This mechanism is domain agnostic. It works for words, but the same mathematical operation can apply to any sequence of numerical embeddings. This leads us directly to how we apply this to images.
From understanding sentences to interpreting pixels, that's quite a leap, but now I see the foundational elements that make it possible.